Delta G is from our second law. Second law of thermodynamics is going to be delta G of the system, delta H of the system, minus T delta S of the system. And so in this form of the second law, if delta G goes down, then we have a driving force. So if delta G is negative. And so we look for things that make this negative here. But what are the restrictions on this particular equation here? Well, it depends on where we get the data. One of the restrictions is a lot of our data comes from appendix D. And so data from appendix D is restricted. In what way?
They're only at certain temperatures and pressures, standard thermodynamic conditions.
Yeah. One, it's standard thermodynamic conditions, which means what? Which means two things.
1 atm, 1 mole, 1
Yeah.
bar.
1 atm or 1 bar. They're very close, just a slight difference. Our table, appendix D, I think is in bars. But other tables will be at ATM. And then, I have to double check that again because gotta make sure that it is. And 1 molar solution, since we're gonna have solutions. The temperature is not standard, but the temperature for appendix D is fixed. The temperature is 298 Kelvin. In fact, there's no standard temperature because, a lot of people don't do chemical reactions at room temperature. A lot of people do chemical reactions at elevated temperature. And so it makes no sense to fix, because some reactions are just quite slow at room temperature. But anyway, we have the driving force here. This is data from appendix D. All right, so when we do our calculations using appendix D data, then we have this delta G naught, which is this under standard conditions at 298 Kelvin, is equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. Well, if the temperature is at 298 Kelvin, then we know what T is. T's got to be 298 Kelvin, right? And so here we can calculate things under standard conditions, that is 1 atmosphere, 1 molar, and 298 Kelvin. And we just use the appendix D data. And so we can figure out what delta H is using delta H's formation. We can figure out what delta S is using the absolute entropies of the substances. This is all for the system. Pretty soon I'm going to drop the system because we know it's going to be for the system, not the surroundings. And that's the nice thing about this form of the second law of thermodynamics. Okay, so if this comes out negative, we say, if it's negative, we say it's spontaneous. There's a driving force. If it's equal to 0, we say it's at equilibrium. If it's greater than 0, we say it's non-spontaneous. There's no driving force. And so this is the way we can balance the energy and the entropy terms. But both terms actually end up increasing the entropy of the universe. We were talking about energy entropy. And so doing a standard calculation is pretty straightforward. You just plug in the numbers, and we'll do an example of that later. Now, this is kind of restrictive, right? Because do we want to do every single reaction at 290 Kelvin? No. But if we don't do, let's see, what about standard conditions at temperatures not equal to 298 Kelvin? Well, if we are doing standard conditions, but the temperature, let's say we just want to increase the temperature, we'll leave this alone. We'll leave it at 1 atmosphere or 1 bar and 1 molar. And so the concentrations, pressures are the same. We just want to increase or decrease the temperature. And then what do we do? Well, then that means we have delta G naught standard at temperature T, which is equal to delta H naught standard at temperature T minus T delta S naught at temperature T. And so So what that means is we have two choices here. That means we're given the delta H at temperature T and delta S at temperature T. That's one. Either one, we're given this, or two, if we don't know the delta H at that temperature, and we don't know the delta S at that temperature, then we're going to assume that delta H at temperature T is about equal to delta H at 298 Kelvin. Okay, this is going to be under standard conditions. Under standard conditions. Now, this assumption is reasonable because I don't know if I mentioned this the other day, but when we're looking at delta H of vaporization, room temperature, we have room temperature water, and then we have room temperature gaseous water, or water in the vapor state. And so the delta H of vaporization is converting the liquid water into the gaseous water, but both are at 298 Kelvin. If we increase the temperature, let's say 50 degrees C, then we have water, at 50 degrees C, but we'll also have the vapor at 50 degrees C. And so when we do that delta H, that is converting the liquid into the vapor state, it's about the same. And so what we can say is this, as long as the temperature isn't dramatically, as long as the temperature isn't dramatically different, like hugely different, where there's a different state or something like that, then this should be okay. We just have to worry, if we increase the temperature dramatically, the state might change. So this is reasonable. I don't have data to show you. It's much better rather than taking my word to look at the observed data and then come up with the conclusion that that's a reasonable assumption.
So we can say that's reasonable where a phase change doesn't occur? Yeah,
as long as you're, you wouldn't, let's say delta H of vaporization of water 298 is the same as delta H of vaporization at minus 300. We can't go that below. Minus 150 degrees C. At minus 150 degrees C, the liquid water is now a block of ice, and so it doesn't make sense at that time to do that. And so we have to worry. Sometimes people don't pay attention to temperature, and then they'll use the value at let's say delta H of vaporization water at 298 Kelvin is the same as delta H of vaporization at 2000 Kelvin. At 2000 Kelvin, is there much liquid water? No. And so we have to worry about that. But for the most part, this turns out to, it's going to lead to a little error, but not a huge error. It's better if we have the data. And the other thing we're going to assume is that delta S naught at temperature T is about equal to delta S naught at 298 Kelvin. And so if we don't have the data at the temperature that we want, then we'll just use the data at 298 Kelvin. And then we have to add a note here. Note, delta G naught at temperature T is not necessarily equal to delta G naught at 298 Kelvin. And in fact, it will not be equal if T is not equal to 298 Kelvin. Delta G naught changes dramatically with temperature. And so these don't, but here, delta G naught, or delta G, actually, delta G doesn't have to be restricted to standard conditions. Delta G under any conditions, this would be, when I put this little superscript here, I restrict it. This is unrestricted, so it could be at standard, or it might not be at standard. But delta G is temperature dependent. And therefore, we can't assume it stays relatively constant. And so this allows us to do certain things. Now, that's at different temperatures. All right. What about non-standard condition? What if we do it non-standard?
Would you ever give us a question where the pressure isn't 1 atmosphere?
Yes.
Okay.
Yeah, I'll do that. We'll look at that. And so we can come up with equations like this. You know, it turns out, what's the easiest way to calculate delta G naught? Let me add this here. Because if we restrict it under these conditions here, then actually there's an easier way to determine it using Hess's law. And sorry, let me insert this here. The easiest way is to do it like we do delta H's. The way we do delta H is we take the delta H's of formation of the products minus the delta H's of formation of the reactants. That works because of Hess's law. Well, the same thing, delta G is an energy, so what we can do is we can just take the sum of the delta G's of formation of the products minus the sum of the delta G's of formation of the reactants. Okay, this equation is only going to work under these restrictions here. This equation we cannot use at other temperatures and non-standard conditions because these delta G's of formation come from Appendix D. Appendix D. And so let's take a look at just these two calculations.
Professor, was that thing before the triangle?
Oh, that's nu, the Greek letter nu. Does somebody know what it stands for? It stands for frequency in chapter 6, but in chapter 7 it stood for something else.
Is it the moles of the product?
Yes, the moles of each.
Moles, yeah.
Yeah, energy, so if you have 1 mole, nu would be 1 mole. You had 2 moles of it, nu would be 2 moles. What the nu comes from, let me just show you here. Nu comes from, you know, when we're looking at the, like delta H, this is back in chapter 7, delta H is a formation here. And so you can just remind yourself what a formation reaction is. It's a formation of 1 mole of substance from the elements in their standard states. And then if we apply this by Hess's law, we can either add up equations, but since all these are formation equations, we can come up with an even simpler equation than that. Rather than adding up equations like this, we come up with this. You know, delta H, under standard conditions for the reaction, is equal to mu P delta H of formation of the product minus mu R delta H of formation of the they call nu here the stoichiometric coefficient, nu. And then sigma is the sum.